Hey everyone, thanks for joining me on another episode of Fascinating Frontiers. I'm Patrick, coming to you from Vancouver, and I've got to say, the last few weeks have delivered some genuinely cool developments from across the solar system and beyond. Today we're diving into everything from the battered metal heart of an ancient protoplanet to the very first dusty steps of planet formation, and even some surprising ways space tech is keeping us safer right here on Earth. Let's jump in. We'll start with one of the most intriguing objects in the asteroid belt, 16 Psyche. This thing is roughly the size of Massachusetts, yet it stands out dramatically because it appears to be made almost entirely of metal rather than the rocky or icy material we see in most other asteroids. For a long time, planetary scientists have suspected that Psyche might actually be the exposed metallic core of a protoplanet that was violently shattered in the chaotic early days of the solar system, before it could finish growing into a full planet. That idea is fascinating on its own because it would give us direct access to the kind of material that usually stays hidden deep inside worlds like Earth. Now, a new analysis of the asteroid's giant craters is adding some real weight to that story. These massive impact features seem to preserve clues about the body's internal structure and history in ways we hadn't fully appreciated before. By studying how those craters formed and what they expose, researchers hope to figure out once and for all whether Psyche really is a stripped planetary core or if it formed through some other, perhaps less dramatic process. Either way, the answer matters. Understanding Psyche helps us piece together how differentiation, the process where heavier metals sink to the center of a growing body, worked among the countless planetesimals that eventually built the planets we see today. It's like having a time capsule from the solar system's rowdiest adolescence, and I can't wait to see what the upcoming NASA mission reveals when it gets there. While Psyche may be the exposed heart of a destroyed world, other researchers are looking at the very beginning of the story, how tiny dust grains first start sticking together in the swirling disks around young stars. A team in Switzerland recently ran some clever experiments during parabolic flights that create those precious seconds of weightlessness we can't easily get on the ground. These flights mimic the near-zero gravity conditions inside a protoplanetary disk, letting them watch in real time how individual dust grains begin to clump and aggregate. What makes this work so compelling is how fundamental the process is. The way those first tiny particles overcome electrostatic repulsion and start forming larger structures is one of the earliest and most poorly understood steps on the road to rocky planets. Ground-based experiments always have to fight against gravity, which changes how the grains behave, so these microgravity flights give us something closer to the real thing. Seeing those first fragile clumps form feels almost magical, like watching the universe take its very first baby steps toward making worlds. It's a quiet result in some ways, but it fills in a crucial piece of the puzzle that connects the raw material of a nebula to the planets that eventually orbit a star. Speaking of watching the universe in action, we're also getting better at catching the dramatic deaths of stars the moment they happen. The team at NSF Noir Lab has just finished end-to-end testing of a sophisticated new alert system designed to work with the upcoming Vera C. Rubin Observatory. During these tests, the system successfully triggered rapid follow-up observations from telescopes around the world and managed to catch 4 supernovae in their earliest moments. That might not sound like a huge number, but it's actually a really big deal. The Rubin Observatory is about to begin a 10-year survey that will scan the entire southern sky every few nights, generating an enormous flood of data. Having an alert system that can spot something interesting, sound the alarm, and get other instruments pointed at it within minutes is going to transform how we study transient events. Catching supernovae while they're still ramping up gives astronomers precious data about the explosion mechanisms, the types of stars involved, and even what kind of material gets blasted out into space. It's a perfect example of how next-generation survey astronomy is turning the sky into a dynamic, real-time laboratory. The fact they already snagged 4 supernovae during testing makes me optimistic about the flood of discoveries we can expect once the full survey begins. Of course, while we're preparing for all this new science from the sky, there's also important work happening much closer to home to keep our space operations safe. The U.S. Space Force has stood up dedicated cyber defense squadrons at both Cape Canaveral and Vandenberg Space Force Base. These new units are specifically focused on protecting launch infrastructure from malicious cyber attacks, something that's becoming increasingly critical as more and more rockets head to orbit. It's easy to think of space launches as purely physical events, rockets, flames, physics, but the digital side is just as important now. A successful hack during a launch window could have serious consequences, whether it's disrupting communications, feeding bad data to ground systems, or worse. Having specialized teams whose only job is to stay ahead of those threats feels like a smart and timely move. It's reassuring to know that as space traffic keeps growing, we're treating cybersecurity with the same seriousness we give to traditional range safety. And speaking of using space technology to protect people on the ground, there's a really elegant new demonstration of NASA's Guardian software. This experimental system watches for tiny distortions in signals from global navigation satellite systems, things like GPS, and can spot the telltale signatures of an approaching tsunami. By tracking how a tsunami's movement through the ocean disturbs the ionosphere and therefore the satellite signals passing through it, Guardian turns the infrastructure we already have in orbit into an additional planetary safety net. The beauty of this approach is that it could give coastal communities a bit more lead time before the waves arrive, minutes that can make a real difference for evacuation and preparation. It's one of those lovely cases where technology originally developed to help us explore space ends up serving a very practical purpose right here on Earth. Every time I see something like this, I'm reminded how interconnected these fields really are. That spirit of connection and discovery was on full display recently at the University of Florida's Marston Science Library. NASA helped host the Emerge NASA Data Hackathon, bringing together students, library staff, researchers, and community members to work directly with real NASA datasets. The focus was on environmental and public health science, showing how the same tools and data used to study distant planets can be turned toward challenges we face here at home. What I love about events like this is how they break down the idea that space data is only for professional scientists wearing lab coats. When you put actual NASA tools in the hands of a diverse group of people and let them explore, you get fresh perspectives and unexpected insights. It's genuinely inspiring to see the next generation and people who never thought they'd touch space data getting excited about the same information that helps us understand everything from climate patterns to air quality. Moments like this make me optimistic about how broadly space exploration can benefit society. While students here on Earth were digging into NASA data, astronomers made a remarkable find in a tiny galaxy far beyond our own. In the ultra-faint dwarf galaxy known as Pictor 2, they've identified a star called Pic-Au 503. This ancient star is more than 10 billion years old and has extremely low metallicity, meaning it preserves chemical clues from the very early universe, shortly after the Big Bang. Stars like this act like cosmic time capsules. Because they formed from the debris of the first generation of stars, their atmospheres carry the chemical fingerprints of those earliest nuclear furnaces. Finding one in a small, quiet dwarf galaxy gives us a cleaner window into those ancient conditions than we usually get in our own busy Milky Way. It's humbling to think we can still read those clues billions of years later, almost like finding a note written at the dawn of time. Staying with ancient cosmic objects, there's an intriguing story involving two objects that never quite made it as stars on their own. Astronomers have spotted two brown dwarfs that appear to be on a collision course. If they merge, the combined mass might finally be enough to ignite nuclear fusion in the core, turning what were essentially failed stars into a genuine, if small, star. Brown dwarfs occupy that awkward middle ground between planets and stars. They have too much mass to be considered planets, but not quite enough to sustain the hydrogen fusion that defines a real star. The idea that two of them could get a dramatic second chance through a merger is pretty wild. It's a reminder that stellar evolution isn't always a straightforward path. Sometimes the universe finds creative ways to light things up. I'll definitely be keeping an eye on this system as more observations come in. Closer to home, analysis of the samples returned by OSIRIS-REx from asteroid Bennu has solved a long-standing puzzle about its surface. When the spacecraft first arrived, Bennu looked surprisingly soft and sandy for an airless body. The returned material now shows that the sand appearance is actually the result of extensive cracking and fracturing throughout the boulders. Those cracks break the rocks down into finer material that gives the surface its deceptively loose texture. Understanding this process helps us interpret data from other small bodies more accurately too. It's another example of how a single sample return mission can rewrite our assumptions about objects we've only seen from a distance. Bennu keeps surprising us, and I suspect we'll be learning from those samples for years to come. Now here's something that really blew my mind when I started reading about it. If you could somehow shrink our sun down to the size of a small Canadian city, say something like Regina or Saskatoon, Its density would still be almost nothing compared to the plasma swirling in the inner accretion disk around a feeding black hole. We're talking temperatures that climb above 10 million degrees Celsius, with material whipping around at a significant fraction of the speed of light. That rapid motion, combined with the black hole's own spin, twists and amplifies magnetic field lines through a process called magnetorotational instability. It's basically a cosmic dynamo on an almost unimaginable scale, capable of launching relativistic jets that stretch for thousands of light years. We can see those jets and even the shadows cast by the event horizon itself, yet the exact mechanism that lets magnetic fields thread right through the horizon remains one of the toughest puzzles in high-energy astrophysics. The fields are so strong they can extract rotational energy from the black hole through the Blandford-Znaiec process, powering some of the brightest objects in the universe. What keeps theorists up at night is exactly how ordered those fields become so close to the singularity. We see the results clearly, but the precise dance of plasma and magnetism at that extreme scale still pushes our best simulations to their limits. Speaking of pushing theories to their limits, the growing catalog of gravitational wave detections from the LIGO-Virgo-Cagra network is being used to test Einstein's general relativity in the most extreme conditions imaginable. Each black hole merger gives us another clean look at how gravity behaves when it's really pushed to the edge. So far, the theory continues to hold up beautifully, but the search for even tiny deviations keeps driving the science forward. It's the kind of careful, persistent work that slowly tightens the bounds on alternative ideas about gravity, and I find it quietly thrilling. On a more practical note, Rocket Lab is getting ready for its 85th Electron mission, nicknamed Daughter of the Stars. The launch will carry the first 2 satellites for ESA's Celeste in-orbit demonstration. These CubeSats will test next-generation navigation technologies that could become part of future European low Earth orbit positioning, navigation, and timing systems. It's a nice example of how commercial launch providers are becoming essential partners in building tomorrow's space infrastructure. Getting these test satellites up now will help secure frequency filings and prove out the concepts before committing to a much larger constellation. International collaborations like this always make me optimistic about how quickly the space sector is evolving. Before we wrap up, don't forget to look up on the evening of March 29th. The moon will pass close to Regulus, the brightest star in the constellation Leo. Even without binoculars, you can step outside and see our nearest celestial neighbor hanging out near a star that's hundreds of light years away. It's a simple but beautiful reminder that the universe is three-dimensional and we get to watch the show from the cheap seats. Keep an eye on the Vera C. Rubin Observatory as more test data rolls in. There are going to be some spectacular discoveries ahead. That's it for episode 44 of Fascinating Frontiers. If you enjoyed the show, a rating or review on Apple Podcasts or Spotify really does help new listeners find us. I'm Patrick in Vancouver. Thanks for exploring the cosmos with me, and I'll talk to you next time. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.
Drifting softly through the black